Everyone, welcome back to my channel EduVibe. In today's lesson, we are continuing the atomic physics with the next topic and the last model of the atom, which is the quantum model of the atom. Like this is the latest model, and we not learn very much in this for the grade 12 physics. We learn just the definition, what's the quantum are, and we do some questions related to this. So, the quantum model of the atom is a modern way scientists describe how electrons behave inside an atom. So inside the atom, how the electrons behave, that model called the quantum model of the atom. Instead of saying electrons move in fixed circular paths like in the older Bohr model, the quantum model says electrons exist in probability regions, not a z path. These regions are called the orbitals. So the Bohr model, which we done in previous lesson, this says that the electrons are like moving in the fixed circular paths. But the quantum model says that they are some existential probability regions. They are not like particular regions of every electron. They don't have any z. They don't have not any z path. The regions are called the orbitals, and they have a different regions with that they not have the fixed regions. So that's the quantum model will say in that case. So you have to just know about these things, like what the quantum model do, and for the gate is you do it in higher studies as what is quantum model in detail. So we have examples. So related to that, we have some examples. So examples are again related to the previous units we did. So determine the t-Borlake wavelength of an electron isolated from rest across the potential difference of 600 volt between charged plates when it reaches the positively charged plate. So they mention the electron isolated from the rest, which means their initial energies at rest across the potential difference of 600 meters charged plates when it reaches from the and it reaches to the positive plate. So if it is reaches to the positive plate, which means they start from the negative plate. So we have a negative plate over there. This is a negative plate, and this is a positive plate. And the electron is over there, and they're reaching towards the positive plate. They said that we have a 600 volts of potential difference. So we have the VA 600 volts. We have VA, but VB is going to be 0 in gaseous. So we basically we have to find the wavelength. This is a dipole wavelength, which is like a photon momentum we did. So its wavelength is equal to h upon p. P is your momentum. So h upon mv, you know the h, which is 6.63 into 10 raised to power minus 34 joules per second. You know the mass of the electron, 9.11 10 raised to minus 31 kgs, but you don't know the v. So you want to calculate the V from this potential difference, and you use the law of conservation of energy in that case. So you know EKA plus EPA is equal to EKB plus EPB. This is it. So we have this, but initially it has rest, so this goes out. And after we have VB, which is the volt potential difference, also 0 after that, so it also goes to 0. We left with this EP, which is Q times potential difference at A is equal to half m VB square. We have to find the VB. So isolate the VB from here, you will get like 2 QVA upon m, this whole. So 2 times, so electrons charges 1.6 into 10 raised to power minus 19 coulombs, and the volt this is given to us, Va is 600 volts, and the masses of electron 9.11 10 raised to minus 31 kgs. This whole root. When you calculate this, you get about 1.451 into 10 raised to power 7 meter per second. This is your VB, and this is your V, so you have to put this over there. So 1.451 into 10 raised to power 7 meter per second. When you calculate this, you get your wavelength of about 5.01. This into 10 raised to power minus 11 meters. So this is your wavelength. So they mentioned they verify the de Broglie wavelength. So this is the formula you have to use to calculate this, and you have involving the plates in this. So you can use the law of conservation of energy to calculate the V. That's all you have to do. And for the next example, we do something else, but again related to the same thing. A lateral orbits a proton at a distance of 1.0 in 10 raised to minus 10 meters. This is 10 raised to minus 10. Resume the electron orbits the proton in circular motion and the intersection governed by the Coulomb's law. So determine its orbital speed and the deeper wavelength after orbiting the proton. So they govern by the Coulomb's law. So what is the Coulomb's law? So this is like a circular motion type thing. They mention that they orbits the proton in the circular motion, which means we connect the Coulomb's law with the circular motion. So for A, you have to find the speed, which is the V. So Fc is equal to the Coulomb's law, which is Fc is the circular force. So it's mv square upon r. This is equal to, so this is involving the proton and the electron. The electron orbits the proton. So we have two things. So here this means we have two masses, two charges. So Qp and the Qe upon r square. So this r square 1 cancel out with this. Basically, when you know that, when you see from your formula sheet, you will see that Qp is equal to charge of proton is equal to the charge of electron, which we take as the Q and the Q square of that. So basically, you have to find the V. So we isolate the V from here, and you will get a K Q square from here and M R. Basically, the electron orbits a proton in circular motion, so we have to take the electron's mass in that case. So this is ME. So now just put the things in. So K is 8.9 into 10 raised to 9 Newton meter square Coulomb square. Q square is 1.6 into 10 raised to minus 19 coulombs. Again, square of this divided by electron's mass, which is this on the formula sheet, and the r is given to you, which is the distance, this one. So 1.6 into 10 raised to minus 10 meters, and the whole root of this. When you calculate this, you get 1.54 something, and into 10 raised to plus 6 meter per second. You want 3 set this, so this is your orbital speed. So you have a velocity now, and you have to find the again the wavelength. So we use the same formula we used in previous question. That wavelength is equal to the h upon momentum, h upon m times v. H you know is 6.63 in 10 raised to minus 34 joules per second. Mass of electron 9.11 10 raised to minus 31 kgs. And you have to use the non-rounded value of the V. So use that value and put it over there. And when you put this and you calculate this, you get about 4.71 into 10 raised to minus 10 meters. So this is your wavelength of that in 3 seconds. So that's how you have to find the questions. Like quantum model of the atom, you just know that I mentioned over there. You have to just know these things. And you have to know some questions linked to the wavelength especially. So the every question is linked to the wavelength in that case. And sometimes you use the other formulas if they mention in the question to calculate some other things in that. So that's all you have to cover in the quantum model of the atom, and that's the end part of the model of the atoms. We completed the atom part, and now we're doing some practice questions of this part. Then we move on to the last part, which is the introduction to the nuclear physics. So this is very important that the main chapter is coming from that part, which is the nuclear physics. So we did in the next video, we do practice question, then we start that topic. But so let me say if you are EduVibe, learn smart not harder. Please like, share and subscribe to my channel. If you have any questions, let me know in the comment section. See you in the next lesson. Till let's get it with EduVibe.